record. Okay, so again, welcome to the digital control class. Now I imagine most of you have taken the linear control class, whether at UWF or whether you've taken it somewhere else. So this digital control class is the next course following the linear control class. So I assume everybody have the basic knowledge of control systems, of modeling, second order response, stability, root locus, filtered, compensator design, controller design. So all these concepts are at least familiar to most of you. Now again, when you know, in this course, I'm going to assume everybody knows these things. So we're not going to go back, for instance, and explain what root locus is or what stability means. Instead, we're going to be applying it as it applies to a digital control system. Nevertheless, if you need help, you know, coming up to speed, or if you feel throughout the semester you're missing something, or there are things that you feel you don't have the background to, feel free to let me know. Okay, so what we're going to be doing today are two things. We're going to be looking at the syllabus and agree on some logistics and ground rules, and then we'll just introduce the topic of the digital control. So with that, let me open my syllabus, which I updated, by the way, and I just posted it. So, and let me share. Okay, can you see the syllabus?
Yes, sir. Yes, we can.
Okay, perfect. Is this the lit? No, this is not the one, sorry. Let me close this. Okay, this is the one we want. Okay. So again, the prerequisite for this class is the linear control systems. And of course, it will help if you have also a background in Z-transform. We're going to be using Z-transform throughout the course. So if you've seen Z-transform, some of you might have seen it briefly in signals and systems. Some of you might have taken digital signal processing, so they're more familiar with it. Nevertheless, the Z-transform is going to be the tool that we're going to be using throughout the semester. Similar to how we use the Laplace transform in linear control class, we're going to be using the Z-transform in the digital control class. Okay, now the first order of business is whether to do this course synchronously or asynchronously. And from the students, actually I got a mixed messages from the students. Lots of the students are working and taking this chunk of their time during the day is going to be something that is really not possible. So lots of the students are not going to be able to meet at this time. And adding to that, the fact that, you know, if we were to meet twice a week, we're going to be meeting for over 2.5 hours. And therefore, I'm worried that, you know, it might be just too long of a lectures to sit in one setting. And therefore, I'm going to suggest that we do this class asynchronously, which means on Sunday, I will be posting modules for the week, and you will be watching the modules. Now, we can also schedule a regular meeting to come together if you like to discuss anything that is not clear, or you can use the office hours, or you can send me to schedule a meeting, and we can go over anything or any questions that you might have. How does that sound for everybody?
Sounds good.
Is that make better than, you know, sitting twice a week? I mean, I know last summer, we did the class synchronously, and that worked. Nevertheless, I don't know, for some reason, most of the people were able to move. I did not hear anybody saying, you know, I'm not able to attend. This class, lots of the students are taking it, are graduate students. many of them are working, and therefore, you know, they're not going to be able to attend the class. Now, it is easier for me to do either synchronously or asynchronously. It is going to be a little bit harder if I do it synchronously but expect people to watch the lecture asynchronously. Does that make sense? Okay, so we'll try the asynchronous method, and please feel free to give me feedback if you feel that, you know, this is really not working, I'm not motivated enough to watch the lectures, or I could not understand anything you're saying, or, you know, I really have lots of questions I would have preferred if we interact. By all means, let me know. And again, I can schedule like a regular meeting either weekly or every 2 weeks, where we can just come together and, you know, go over material or questions that you might have. Again, I'm available. I mean, whatever works for everybody, whatever you will get most out of this class, you know, I'm here to help you and facilitate that. Okay, so we're gonna try the asynchronous method. On Sunday, I'll be posting modules, and hopefully I will try to make them clear as to what the module is. And the advantage of doing the modules is that I can make them shorter or longer. So we can have, and I will try to also limit the module length to as short as possible. So I will stop at either half an hour or 45 minutes. So the module is self-contained and it does not really take, you know, that long to watch and to go over. Okay. Now again, I'm available during the class time. I put office hours noon to 1 on Tuesday and Thursday, but I am available most of the time. And usually from experience, students will email and, you know, ask a question, and I feel it can be answered by email, I'll answer. Otherwise, I'll schedule a meeting and we can go over it over a meeting. So again, if you contact me because you have a question, please send me the question and tell me also what time you're available, because then I can look at your question and see if we really need to meet, or we can just do it over the email, depending on, again, the question or the issue. Okay, the textbook that we're going to be using is the Digital Control System Analysis and Design, and it is by Phillips, and I think it's a good book to have. I'm not sure how many of you are going to be buying the book, how many are going to be relying on the handout. It's up to you. I'm not telling you to buy it or not buy it. If you can buy it, that will be great. I encourage you to buy it. And again, I repeat this every class I teach. The good thing about having the book and becoming familiar with the book is that you can access this book anywhere in the world. So you could be traveling overseas and you have an important meeting and you're going to be discussing something and you remember, oh, this topic we might have covered in digital control, but I don't have the handouts from the professor that taught me that class. Oh, but I have the textbook. You can go to any bookstore, to any library, and get the book, and it's going to look exactly the way it looked when you studied it. And I mean, I argue too that once you're familiar with the book, once you look at it again, even after a period of time, it will be much easier to go back and, understand the parts or, refresh on whatever topic you want. Nevertheless, when I assign homeworks, I'm going to post the whole problem. So if you feel like, oh, do I need to get the book because of the homework? I'm not going to write the number of the problem. I'm going to list or type the whole problem. And therefore, you should be able to do the homeworks, based on the description of the problem in the handout. Okay. Now, for the grading policy, my plan is to have 3 exams. Now, last semester we tried 3 exams and take the highest 2. Potentially we can try something similar here. The problem what happened last semester is some students, after they got 2 good exams, they decided we can skip the class or we can not follow the class. And that, that that's why I'm not writing here that we can skip one exam. So we'll have 3 exams, a first, a second, and a final. Now I realize the summer is a very fast semester, and even time flies faster in the summer. And I know lots of you might be already overwhelmed with their projects, with their with their other classes, with their thesis, with their work, with their family affairs and business, and therefore, are you having audio problem? Can everybody hear me? Okay. You see, that's the other problem with also the problem with the synchronous. If anybody is having an audio, if I'm having an audio or internet issue, it becomes like really more stressful than it should be. Okay. Sounds good? Now we have students who are undergrad and we have students who are a grad. And I thought what we will do is we'll add some extra work to our grad students, and therefore we'll assign also a project to the grad students. So for the undergrad, they don't have to do a project, it's optional, but for the grad students, they will have to do a project. Sounds good? And with the project, hopefully we'll give you, hit time on it. We'll see whether we'll have everybody doing the same project, or if somebody is already working on a problem in digital control and they like to bring it in as a project for the class, they're more than welcome to do that too. So there is some flexibility. We have some hardware that we obtained for our intelligent lab that I'm hoping some of the grad students will help set up some experiments that we can do with the hardware that we have. We have data acquisition, we have some motors that we should be able to control, and therefore we can have some grad students doing this work as project for this class. Okay, feel free please to chime in if you have any input, any questions. Please feel free to ask, to interact. If you do not interact, then that will support the argument that asynchronous might be better. Okay. Now you are familiar with the linear control. Most of you have taken linear control. So what this course is going to be doing is we're going to be doing similar topics to what we covered in linear control, except we're going to be doing it with a digital controller. We're not going to be dealing with continuous time signals or system, but rather we're going to be dealing with discrete and digital signals. And therefore, because we are dealing with discrete and digital signals, all the analysis tools are going to be different, and all the performance calculations are going to be different, and therefore we're going to be using new tools and to analyze and to design our controller. Nevertheless, I mean, in the back of your mind, you can still remember the progression of how we done the linear control. We're going to start if you remember, in linear control, we start modeling the system, then we reviewed Laplace transform, then we start looking at flow diagrams and block diagram reduction, then we start calculating open loop, closed loop, the response of the system, stability, root locus, and then design of a controller. We're almost gonna follow something similar with digital control. Again, with all, replacing all the Laplace analysis with the Z-transform analysis. Okay. Now here is a tentative course outline and schedule. So we'll try to, as much as we can, to stick to it. Nevertheless, we might not be able to 100%. I mean, I know we have holidays coming in, and we might have, you know, exam week, etc. So there might be some interruptions to this. Nevertheless, we'll try to update it as we go, and nevertheless, this will give you a good idea of the topics that we're going to be covering this semester. Okay. Can I ask you, just to have more interaction, how many of you are from electrical engineering, and do we have anybody from mechanical engineering?
I'm electrical.
Any
I'm
mechanical?
I'm electrical.
Okay, most of you are electrical, mechanical, okay. Nevertheless, everybody have taken linear control. Now again, this course is as essential to electrical as it is to mechanical engineers. I mean, you know, we have a common interest in doing a control problem and a control design and integrating moving objects with an electrical signal to get a control system. Okay. Now, just I want to mention that we're going to be using analog in our exams, and this is out of redundance of caution. If you have any problem with analog, please let me know. Nevertheless, I think it's a good idea to ensure the integrity of the exams for everybody's peace of mind, and therefore we'll be using analog. I know we had some issues with it. Some students will have problems with it. Nevertheless, I mean, I'll be, if you have any issues with it, let me know. If you have any issues before we start, let me know. And again, during the exam, I mean, hopefully we'll have a meeting. If you have anything, I'll try to help you move through it. Okay. Any questions? Any comments?
Will this course run the full semester?
I think that is the plan.
Okay.
That is the plan.
That's good.
Yeah. I mean, knowing how, I mean, we are already a shorter semester than usual. Now, last semester, last summer, we tried to squeeze in more time in each lecture and try to finish shorter. But since this is asynchronous, I mean, and you have the flexibility. So if anybody is traveling or if they have some other plans, they can still do it. And while attending, you know, the same, I mean, that's the advantage actually of the asynchronous method, is it will give you the flexibility of the time. If you have plans after summer or before the next semester starts, then you will be able to still do it. What is the form of the exams? Yes, the form exam, it's gonna be I mean, 1 hour, unlimited, either way. I mean, there is some flexibility. We'll see. We'll either do the exam during the class time or we'll do it off the class time. And again, since some students are not able to join during class time, it might be harder to join during the class time. Is that, and that might create also another issue, which is you might have to take the exam on your own. Does that make sense? So if we do the exam during class time, usually I will have a meeting and I'm available to answer questions. But if I might just post the exam online and tell you, please take it between, I don't know, 4 o'clock and midnight. And you might have 1 hour or 1.5 hours to finish the exam. Usually, I mean, knowing this exam, it might be most likely 1 hour, 15 minutes for the exam. And what I'm thinking is this semester is to have the exam as open book and open notes. Does that answer your question, Josh? Okay.
About how many questions would we expect on the test?
Probably, like usually I have 2 or 3 problems but they may have multiple parts. Nevertheless, I mean, if anybody needs more time, or need any other accommodation, please let me know. I mean, we can work together to do that. I usually do not like to restrict the students with the time, especially when they're doing it remotely like this. I mean, it's stressful as it is to do the exam on your own when you're connected to the internet. And I have actually one of my kids taking an AP exam, and the minute he wanted to submit the exam, the computer froze and he could not turn it in on time, and he could not submit the exam. And I've seen it. I was sitting next to him. I mean, I was sitting at my desk working, and I saw him getting stressed. And that was a learning experience of what probably some of our students might be going through. So again, the exam is not going to be stressful. The logistics are not going to be stressful. If anything happens, just let me know. We'll fix it. So I don't want anybody to be stressed over how I'm going to be taking the exam. My internet is slow. What happens if I get disconnected? What happens if analog did not work? What happens if the camera does not show me? You don't need to worry about all that. Make sense? I just want you to worry about the problems inside the exam. And all the other ones is not for you to worry about. You're going to do your best, and if there is any issue that comes along the way, we'll work it out. Sounds good?
Sounds good.
Yeah, I think it helps to have one of your kids taking an exam and seeing what they go through when they try to submit the exam and they're running out of time, and it tells you cannot submit after you studied for weeks and ready for the exam. So I don't want anybody to go through that, and hopefully nobody will. Okay. Now also we'll have homework assignments. Now we have the option of turning in the homeworks, and we have the option of not turning in the homeworks. Which one you prefer, turning in homeworks or not? Submit?
Yes, submit.
Turn in. Okay, sounds good. Now, nevertheless, this is a very fast semester. So we'll have hopefully a weekly homework. So just make it, just add a time in your schedule over the weekend or whenever you review the material to be doing the homework and submitting it. And submitting, your solutions. Now, hopefully, yeah, I know. I think that's a good point. Yes, submitting will motivate people to review the material, make sure they're up to speed. And usually, we'll have the homework such that if you really do the homework, then you're in good shape for the exam. Does that make sense? So I'm going to select the homework problems that really will help you prepare also for the exam. Sounds good. Okay. So I have the syllabus online. Please feel free to look at it. If you have any questions, feel free to let me know. Okay, so that was our first order of business. And moving on to our, let me move the chat somewhere. Okay, so just moving on, just introducing the topic. Now I have already recorded some modules that I posted online. Now what I'm going to be doing is I'm going to post the handouts and I'm going to be posting the recording. Now the expectations, actually maybe I will post the recordings and the handouts by weeks. So week 1, week 2, week 3, week 4, week 5, week 6, etc., etc. Does that make sense? So the expectations within that week, you should be reviewing looking at the handouts and watching the videos within that week frame. and I'll try to organize it accordingly, like according to week by week. It probably makes it, I tried to put it by topic, but it might make more sense to have it by week, and probably I will add as a subtitle the topic. Okay. So our objective in this course to review or to study the concept of sampling, discrete time signals, analysis, synthesis of digital control systems. Upon the completion of this course, you should be able to construct a discrete time models of systems. You should be able to design a digital controller, and you should be able to analyze and study an open loop and a closed loop system and study their behavior. This is the textbook that we're adopting. And again, there might be a soft copy of this. It might be a hard copy at the library. Feel free to look at the library. Take it for a few hours if you need to and look at it. And try to get it if you can. Okay. Let me make this maximum screen. Okay. Okay, I want to welcome again people who joined in, and I just looked, it was telling me people are in the waiting room. I had to change the configuration so there is no waiting room, so you can come in on your own. Nevertheless, we're switching to Zoom this semester in this class and in all other classes. And you know, after we mastered the WebEx and we knew everything about it, we're learning a new tool. Nevertheless, we can't complain. That's part of how we are as engineers. We can always learn new things and master them. Okay. So let's look at this diagram. And what we're going to be doing till the rest of this presentation is just introducing the topic of digital control. So if you look at the block diagram that we have on the upper left, this is the analog control systems that we are familiar with. We have a command input of how high I want my elevator to be, or how high my temperature has to be, or how fast my car or my speed needs to be. And then I have a plant, which is the system that I'm trying to control. I have sensors that take measurements of the output and feed it back. And I have my controller. Now this configuration, if you remember, we call it feedback loop. Nevertheless, not every control system has to be with a feedback loop. We can have an open loop control system. I can just have a controller where I do not get a feedback. And if you remember some examples, if you have a toaster oven that you just turn it on, that's an open loop system. It turns on, the bread or the bagel might burn. You have no feedback that will regulate whether it is on or off or the temperature. Nevertheless, having a feedback provides lots of advantages. If I'm trying to control any signal or any output, and I have a measurement of that output, then I can compare it to what I really want it to be, and then apply a signal accordingly. And this is what we get with the feedback loop. I can take the measurement of the output, the speed of the car, the height of the elevator, the temperature of the room, whatever the signal that, or whatever the value I'm trying to control, and I can compare it to my command signal where I want it to be. And if they do not match, I'm going to get an error signal. Now I can take this error signal and apply it directly to the plant. Nevertheless, in doing so, I might run into problems. What potentially can go wrong if I just do it with an error signal and get rid of this controller? Anybody? Do we really need the controller in our feedback system here? I mean, potentially I could have a system that is unstable. So I could have the plant that if I apply any error signal to it, it's going to go out of control. It's going to be unstable. So therefore, I might need a controller to stabilize the system, the plant that I have here. I might have a plant that I want to control how fast the output of that plant or that system moves. If I have an elevator, it's not acceptable to be moving 1 foot every 5 minutes. I need it to go faster. If it's a temperature, it might not be acceptable to change the temperature, and if I want to change it by 1 degree, take 24 hours to change that temperature. So therefore, I'm going to need the controller to make sure the system is stable. I can stabilize the system. I can also make the system control the transient response of the system, which means I can make the system faster or slower according to how I want the response to behave. I can add to or remove or add or remove or tolerate some overshoot in the response of the system for the sake of making it faster. I might not be able to tolerate an overshoot in the system response to make it faster. I also want to make sure that the error signal in the steady state is as small as possible. So if I have a command input signal that is set at 5 volt, for instance, and the output is a volt, I want it to be as close to a 5 volt as possible. So these are the 3 things that we're always concerned about when we talk about a control system: the transient response, how fast the system responds, and the shape of that response. And if you remember, when we studied linear control, we looked at the second order system because it showed us all that behavior. It shows us the overshoot, the oscillation before it reaches a steady state, the rise time, the settling time. All this is part of the transient response. Now, different systems might tolerate a different or might accept a different transient response. If I'm trying to move a motor, I might be able to tolerate some overshoot for the sake of having it move faster. But if I am designing a controller for an elevator, it's not acceptable for the elevator to overshoot and then settle down to whatever floor that you set it at. So again, the system that you're designing for will determine what transient response is acceptable and what is not acceptable. And again, if you remember from linear control, the second order system, the nice thing about the second order system is it was the minimum order system that will show us all this dynamics, all these different behaviors. Remember zeta, damping ratio, overshoot, undershoot, overdamped, underdamped, critically damped. So all this behavior can be obtained or can be studied using a second order system. Okay. Now this is all good and great, and we've done all this. Now what we're gonna do is we're gonna move from designing an analog controller to designing a digital controller. And what that means, instead of building an RC circuit, or if you remember when we discussed, or if you remember when you studied the controller design, we said the controller is implemented using an RC circuit. We can have an active circuit or a passive circuit. We might have an op-amp to generate whatever transfer function of the controller is. And now what we're going to be doing is we're going to be implementing that controller using the computer. And therefore, we're going to be implementing a digital controller. So if you look at the graph, right, actually let's go all the way to the graph at the bottom and then go to the one in the middle. So now what I want to do in this class, I want to be able to take a command signal. I'm going to take the error signal that I obtained. This is still analog. I'm going to take an analog to digital converter. I'm going to feed it to the computer, and I'm going to let the computer algorithm decides how the signal that should be applied to the plant. And therefore, the computer is going to calculate the best signal that can be applied. And then I'm going to take that signal through a digital to analog converter. And then I'm going to apply it to the plant. Make sense? So I'm removing the controller, the analog controller that I have at the top here, with analog digital converter, with an algorithm, with a computer. So this is, as we will see, this is an algorithm, it's the digital controller, it's the compensator, it is a filter. All these names refer to the same thing. Filter, compensator, controller, algorithm, they all refer to the same thing. How to take the signal, the digital signal that I received here, generate a digital signal at the output here that will meet the design specifications, that will meet a performance specifications that I'm trying to implement. Okay, so if you look at this system that we have at the bottom of the page, we have the command input as an analog signal, and we have the plant operate with an analog input. The output of the plant is an analog input. In the middle, I took the signal from the command, the signal from the sensor, subtracted them, convert them to a digital, fed them to a computer, to a microprocessor, to a microcontroller, implemented an algorithm, and then generated a signal, put it through the digital to analog converter, applied it to the plant. Now what we can also do, I mean, this is one configuration, we can do this. Another configuration, we might have the command already in a digital format. And therefore, this is the block diagram that is in the middle. I might have the command already in a digital format. This is what I want if I'm using an autonomous car. This is the speed. I'm gonna be inputting it using a keypad, and this is a digital, already a digital signal on the computer. And therefore, in this case, I'm gonna take the output. The output is gonna have a sensor. Assuming the sensor is analog, I'm gonna take an analog to digital converter, convert it to a digital signal, and this digital signal is gonna be fed through the computer. So all this, let me use all this part is inside the computer, or the microcontroller, or the microprocessor. So this is all the computer. The command is set. I'm gonna feed to it the sensor data, convert it to a digital format, process it, have an algorithm, a filter that will generate a signal, take the output of that filter and apply it to my plant. Make sense? So this is another configuration. We're gonna be looking at many other configurations throughout the semesters. So nevertheless, the point I'm trying to make is there isn't one configuration where we just take the controller, replace it with analog to digital controller, digital to analog. We might have a configuration where the computer is controlling the plant. And therefore, actually I made a mistake here. This sensor, this is the computer. The computer part. So the plant, and you have a controller that generates a signal, and it senses the signal, and the command signal is already part of the computer, a part of the program that you're trying to control. Does that make sense? Together, everybody? Okay. Now, I mean, somebody might look at this and say, okay, I mean, what do we need the whole semester to do this? I mean, we already designed the controller. Why don't we just convert it, analog to digital converter, digital to analog converter, take that controller, try to convert it as much as possible into a digital equation, and we're done. And the answer, I mean, that is one way of doing this. And the other way is to do the whole design using the discrete time systems. So one way we can do all this is do a design, an analog controller design, and try to convert it as accurately as possible to a digital controller. That might work. The other approach is to design the controller for a discrete time system. And that is what will require us to spend the whole semester, because all the analysis that we're going to be doing will be applied to a discrete time system, and therefore it will be different than the analog system that we're familiar with. Now, of course, somebody looking at this might immediately realize, oh, we are sampling here, and we are sampling, and then we are generating an analog signal. And I remember, if I've taken digital filters or digital signal processing, if I sample a signal and design a filter, if I were to change the sampling time, the whole filter behavior is going to change. So that adds another layer of, I don't want to call it complexity, but another layer of understanding to what we need to be doing. When we sample a signal and we design a controller, that controller is going to work for that sampling time that we chose. If we change the sampling time, then the whole system behavior is going to be different. And therefore, that is something also to keep in mind when we are studying the digital control. Everything is designed, everything is going to be dependent on the sampling time. And again, if you remember from when you design a digital filter, if you designed a low-pass filter for a signal that is sampled at 1 kilohertz, if you go apply this low-pass filter to a signal that is sampled at twice at 2 kilohertz, then the whole filter behavior is going to be totally different. The cutoff frequency, all of these things are going to move according to the signal, to the sampling time that you're using. Again, we're going to be discussing these and emphasizing it throughout the semester. Okay, so what are the advantages of a digital control system? I mean, first advantage is the reduced sensitivity and increased robustness. Unlike an analog signal where I can have a signal that might have a noise that gets picked up on it, if I generated a signal that is going to drive an actuator or the plant, and for some reason there is a noise that is added to it, I cannot separate the noise from the analog signal. However, with a digital signal, it's a zeros and ones. So even though if my signal, represented by a voltage within the range that will be decoded as 1, then it can have any noise and still be decoded as 1. And of course, I can always, make sure the signal is correct, with error detection or error correction, etc. So we are, with a digital signal, we are less immune to noise. Think of any analog signal. If you add any noise to that signal, you cannot differentiate the original signal from the new signal. Take a digital signal that is a 1 or a 0. And if, for instance, this digital signal, if it is below 2.5, it's a 0. Above 2.5, it is a 1. The signal can be 0, can be 0.1, 0.2, 0.3, 0.4, 0.5, and still decode it as a 0. Also, with the digital controller, if I have components, the components are always going to behave consistently. Unlike the analog components, where they might heat, they might with time, lose their accuracy. With a digital system, the system is going to be always robust, behaving similar to how it would behave all the time. Another advantage of a digital controller is better adaptability, and that means I can have a digital controller that can have parameters that can adapt to a varying plant conditions. So if I have a controller, I can design the controller to behave differently depending on I can have multiple algorithms that can be applied according to the error signal that I'm measuring. Or I can have, for instance, imagine I'm having, I'm controlling, for instance, I'm controlling an object that might be exposed to environmental conditions. I might have a census data that tells me, oh, the temperature is too hot, the temperature is too low, and depending on, you know, these extra parameters that I have, I might be able to apply different controller to the system, and that is something that you're not going to be able to do with an analog controller. You can automatically adapt to a changing plant or to a changing environment conditions. Another advantage is the form factor. Digital devices are compact and lightweight, and also they are becoming lower and lower cost. Of course, I mean, you imagine everything is moving to a digital controller. Think of, you know, airplanes, controllers, think of autonomous cars, think of all these smart devices that we have with the IoT, your refrigerator, your washing machine, your any of the appliances that you have. All of these will have a digital controller that is used in them to control any of the parameters that the user will wish. And again, the fact that these controllers are so cheap, it is possible to integrate them almost with any device with a very little increase in the cost of that device. Okay, another advantage of the digital controllers is that they are, I mean, more reliable, and I mean, we talked about the robustness, but the other advantage of the digital controller is that their parameters do not change with time. Okay, what is the drawback of a digital controller compared to an analog controller? We're going to have to deal with quantization, and we have to deal with sampling. Now, if you have an analog signal, then the signal, you have a value throughout any point in time. If you look at any signal, continuous time signal, you have lots of data at any point in time. If I'm dealing with a digital signal, then I only have the values at discrete points in time. And we'll see that in a minute. Now, that is already a loss of information, isn't it? If I have a signal that is continuous, I mean, let's see, we'll come to it, but if I have a signal that is continuous, that is defined all the time, versus a signal that is discrete, that is only defined at discrete instance in time, there is some loss of information. The other thing, in order to be able to feed that signal and process it on a computer, the signal has to be quantized, which means I'm going to have a signal that could take on an infinite values, and say I can only take on, I only have, for instance, 6 bits to represent the signal, or I can have 8 bits to represent the signal, and therefore I might have a 128 at 256 levels, and that's all the levels that the signal is allowed to take. And therefore, if the signal happens to be at the exact level, that's great. There is no loss of information. Nevertheless, if the signal is within the range that there is no a quantized level that fits it, I'm going to approximate it with the closest quantized level. We'll see this later on, but I think the idea is, because of that, I'm going to be losing some information that relates to the value of this signal. Okay. So some examples of digital control systems: an aircraft turbojet engine. We can have the pilot on the computer enter whatever settings they want for parameters to control the aircraft. Digital to analog converter that will drive a turbojet engine. We have sensors that take from the engine. We have sensors that come from the aircraft, and we take the analog digital converter and we feed them to the computer. So you see already here a different configuration than the two configurations that we've seen before. here I have, you know, this feedback, and I have another feedback with analog to digital converter, and this is all the command, and the signal is generated using the computer. Another example in medical applications, if we have a drug delivery, again we have a computer with a reference level, and we have a patient where we measure using blood sensors whatever drug that we're trying to apply, and the computer will measure and compare and, you know, decides on the signal that needs to apply to the drug pump, and the signal that comes from the computer is converted using digital to analog converter, and it is applied to the drug pump that is applied, that is administered to the patient. Okay. Okay, I hear something. I'm gonna mute everybody. Can I? Or can you mute yourself if you have some noise coming? Okay. So let's look at discrete time systems. Some definitions. A dynamic system. What is a dynamic system? Is the resistor a dynamic system or not a dynamic system? Who knows if the resistor is a dynamic system or not?
Not.
It's not. Why is it not? Because the resistor does not have a memory. You apply a current to it, gives you a voltage. It does not have any memory. It does not remember what happened when you changed. If I apply the current now and apply the current in 5 minutes, the voltage is going to change and have no impact the previous current that I applied. Systems that have memory, they will create a dynamic system. An inductor, a capacitor, all these will have memory, and what you will get at any time will depend on the initial conditions, and therefore we have the derivation, we have derivative, we have integration to calculate the response of that system. So therefore systems that have memory are dynamic systems, and usually we describe the behavior of that system using differential equations. If they are continuous time signals, systems, we use differential equations to describe them. And if you remember, in control systems, we looked at different mechanical systems and different electrical systems, and we were able to get a model of a system, of a mechanical system, and of a circuit, and we used the differential equations in order to obtain a model of that system. Now, out of all these dynamic systems, there are systems that are linear, and the systems that are linear are the systems that obey superposition, and therefore if I have a signal that I applied to that system and I got an output, if I were to apply another signal, get another output, then if I scale the signal, the first signal, and scale the second signal and add them together and apply them, then the output is going to be the scaling of the first signal multiplied by the output plus the scaling of the second signal multiplied by the output. Homogeneity and additivity. If the system is linear, I imagine everybody is familiar with linearity. Nevertheless, I mean, it's always good to refresh on these definitions. A linear system, you double the input, you're going to double the output. You apply two inputs, the output is going to be the output of the first input plus the output of the second input. Linear system. We like linear systems because linear systems are much easier to study, and there are lots of tools that we can use that we apply to them. Does that make sense? That's why we like linear systems. Now, what do we do with nonlinear systems? We can do nonlinear analysis, or we can always take the nonlinear system and try to linearize it. Find, a point in its operation where it behaves almost linearly. Make sense? Okay. Now, out of all the linear time of the linear systems, the linear dynamic systems, we are also interested in the linear time invariant systems. And the linear time invariant systems are the systems that, if I were to look at the systems, the parameter of that system does not change with time. So therefore, if I come to the system and apply an input today and I get an output, if I come tomorrow, apply the same input, I'm going to get a similar output that I would have gotten when I applied the input yesterday. This system, we call it linear time invariant system. The parameters of the system do not change. And therefore, again, because the parameters do not change, this also enables me to apply lots of the tools to study and to analyze such systems. If the system parameter is changing with time, it will make it much harder to study that system. Okay, so in this course we're going to be focusing on the linear time invariant system. The system parameters are fixed in time and the system is linear and therefore obeys the superposition. Okay. Now we are all probably familiar with both, with the continuous time system and discrete time systems. A continuous time system means we're using differential equations, we're using Laplace transform to study. A discrete time system means a system that we use difference equation to describe, and we use the Z transform as a tool to analyze. The continuous time system, all the variables are continuous in time, defined at any point in time. A discrete time system, the variables are only defined at discrete instance in time. Okay, so if I look at a system that is a discrete time, then we're going to be using a notation that looks something like this. U1 of k as an input produces y1 of k. Again, these are only defined at k, where k is 0, 1, 2. These are the instances where the signal is defined. And if the system is linear, then if I applied a1 multiplied by u1 plus a2 multiplied by u2, I would get a1 multiplied by y1 of k plus a2 multiplied by y2 of k. Okay. Some definitions as we move forwards. I mean, probably these are already familiar. We can keep referring to or using these terms. The plant, which is the physical system or the process that we're trying to control, we'll always refer to it as the plant. We have the sensor, which are the devices that measure the various signals in the plant. And usually, if you remember with the feedback loop that we looked at, where is this loop coming from? It's coming from a sensor. So this is my sensor. It takes the output, a measurement of the output, and it feeds it back. Does anybody remember what we said in linear control about what is different about this sensor, about sensors? Okay, I'm going to tell you and keep that in mind. Sensors are usually very fast. So almost they act instantaneously. And therefore they do not have any dynamics. And therefore, when you look at the loop in the feedback, most of the time, what does the feedback loop look like? It looks like just a line. And somebody might be wondering, oh, I mean, we have all these dynamics in the plant, but then the feedback, why is it always 1? Remember, this is G, this is H, and H, most of the time, what is it equal to? A 1. Why is it equal to a 1? What does equal to a 1 mean? It means two things. It means, of course, it's a scalar value, but that doesn't matter because I can always rewrite this feedback loop and make it a 1. The scaling is not what I'm talking about here. So this 1 could have been 5 or 10 or 100 or 0.01. That doesn't matter because I can move it around to make it a 1. But the more important is that this H usually is very fast, and therefore there's no dynamics in it. I do not have H equal, for instance, 1 over S plus 5. If the system has a transfer function like this in the H, it means the sensor is not instantaneous. It has some dynamics that I have to take into account. Does that make sense, everybody? So when it is a scalar, that tells me that sensor is very fast. Now that makes sense because if I'm designing a system and I'm trying to control a system, I'm going to go find a sensor that is much faster than the system I'm trying to control. It will not make sense if I'm trying to control a motor and I want to measure the motion and go a sensor that is going to give me results that is slower than the motor I'm trying to control. If I'm trying to control the motor and I want it to move, you know, pi over 4 in 1 second, then I'm going to get a sensor that will give me a measurement in millisecond or microsecond. And therefore, the speed of the sensor is much, much faster than that of the system. And therefore, I can just approximate it by a constant. Is that clear, everybody? Okay. Just keep that in mind, because you're gonna, again, seeing it throughout, and you're gonna see always the feedback as 1, and you're gonna forget where it's coming from. Like, oh, why is it we always have a feedback of a 1? The feedback of a 1 basically is saying I have a sensor that is measuring the output, and this sensor is so fast that there is no dynamics in it. It's just acting like the resistor acted. Very fast, gives me instantaneously the measurement. Okay, so then we have the controller. The controller is an algorithm embedded in the physical system that controls the behavior of the plant. Now this controller, again, we're going to refer to it as a controller. We're going to refer to it as a compensator. We're going to refer to it as a filter. They all refer to the same thing. Controller, compensator, filter, they all refer to the same thing. Feedback signal, the signal from the plant entering the controller as input producing desired transform signal that can be that control the plant. So this is our feedback signal, the signal that is the output of the sensor that is fed back. And then we have an actuator, which is the physical device that actuates the controller to take action on the plant. So if I'm trying to control a position, for instance, of an object, then the actuator will be the motor that is going to move that object. Okay. And a closed loop system, the combination of all these elements give me this closed loop system. And remember, when we studied control, we looked at open loop systems, we looked at closed loop systems, and the advantage of the closed loop system is that we get feedback. So I am aware of the state or the status of the output as I am controlling it. With the open loop system, I have no idea what the output is doing. Okay. So also, if you remember, when we study control systems, or when we study any system that we're trying to analyze or design, the first step in studying the system is trying to model the system. And therefore, I want to get a representation of that model of the system. And what we usually use is we use a mathematical model that relates the input and the output of that system. Where do we get this mathematical model? We can get it from analytical analysis. We apply the physical laws, whether it's motion, Newton's laws, whether it is a circuit, Kirchhoff voltage laws, current laws, any analysis tools and techniques to get a relationship between the input and the output. Now we can always use the computer or using numerical analysis to get a relationship between an input and an output. We can always do experiments to get a relationship between an input and an output, applying different input, measuring the output, and try to model it using these measurements. Now what we've done, I have in the modules, in the one that I posted that we're going to be covering this week, is the different models that we use to represent the system. So if you remember, we can use ordinary differential equations. We can use a transfer function. We can use all block integrator diagram to represent the system, and we can use state space representation to model the system, to represent the system. So the model has different representation. So all these are representation of the state system, and we can go back and forth between one and the other. Sounds good? Now, since in the control we only introduced the state space representation, what I'm going to do this week is to focus more on the state space representation, because we're going to be using state space representation in this course throughout the course. So the modules that I'm going to be post will bring you up to speed with the state space representation and how we go back and forth with different representations of the system, and how we can calculate the output of the system if we have the state space representation, and some characteristics and performance that we can get from the state space representation. Okay. So again, looking at the signal, if you remember, if I take an analog signal and I want to convert it to a digital signal, I'm going to have to do two things. I have to sample it and I have to quantize it. And therefore, I can have, if I look here, I have four signals. The signal at the top is an analog signal. It's continuous in the time. It is continuous in the time domain, continuous in the magnitude. The magnitude can take on any value. Now I can take the signal and sample the signal. Now the signal is continuous in the magnitude. The magnitude can take on any value, but the signal is only defined at discrete instances in time. Now also I can take this signal and I can quantize it. Take these samples and just say I'm going to have a finite set of values that the signal can take. And in this case we have 1, 2, 3, 4, 5, 6, for instance 6 levels that the signal can take. And therefore I'm going to approximate each level of the signal when I sample it by the one that is closest to it. Now if I combine the sampling and if I combine the quantization and the sampling together, I'm going to get a digital signal. So if I combine sampling and quantization, sampling and quantization together, I'm going to get a digital signal. The digital signal is going to be defined only at certain instances in time and is going to take on a finite set of values. And therefore, I can import this signal to the computer and I can take it and I'm going to have a sequence of numbers. So this signal, I can go to MATLAB and say X is equal to 0, 0, 0, 0, 1, 1, 1, 0, 0, or I can put the decimal equivalent of this signal this is 0, this is 0, 1, 0, 2, 3, etc. Does that make sense? Now keep in mind that this sequence X is just a sequence of numbers. It does not exist physically anywhere, and we'll emphasize this later on. This is a sequence number that resides in the computer, or that resides in the memory. I cannot measure it, I cannot feel it, I cannot sense it. In order for me to measure it, feel it, or sense it, I have to take it and use a digital to analog converter to convert it to an analog signal. Make sense? Again, we'll emphasize it when we get to it. And some of these things might be clear, and nevertheless, when we are in the middle of the class, I mean, somebody might look at the system and say, oh, what is this signal? Where is this signal coming from? How is it? How do I measure this signal? So I just want to make sure everybody is clear on these things. And the point, again, I'm trying to make is this sequence, when we get the digital signal, we feed it to a computer. That signal physically does not exist. I cannot measure it with the oscilloscope. I cannot measure it with a voltmeter. It only exists on the computer. It's a sequence of numbers. And therefore, if you look, for instance, at the audio file that you have, if you have a wave file, the wave file on your computer has the sample values. It has a parameter that tells it what the sampling frequency of these sample values. That signal, you cannot hear it by its own. You cannot see it. You can see the values, but you cannot generate it unless you use a digital to analog converter. You can play it. When you play it with a wave player or with an audio player, it's going to take these sequences and convert them to an analog signal. Then you will be able to use them. So this sequence resides again inside the computer. For it to leave the computer, I have to put it through a digital to analog converter. Okay, so again, keep in mind, analog signal, continuous in the magnitude, continuous in the time, digital signal, discrete in the time, and discrete in the magnitude. Takes on only a finite values, and it's only defined at certain instances in time.
Question?
Go ahead.
Does those numbers in the digital numbers down there actually relate to that digital signal?
No, they don't.
Okay.
No, they don't.
How in the world did you get those numbers?
Oh my gosh, if I knew somebody is going to be looking that closely at it, I would have modified the numbers, but no, they don't. No, they don't. Okay.
That makes me feel better that I couldn't figure out how they related.
No, I mean, this just, I see what you're saying, but this is just meant to show, how the numbers are stored. And therefore, these are just numbers that exist on the computer for the signal. Okay. Okay. Now, also, probably mention one thing here before we move to the next slide. And of course, if you remember, when we sample the signal, we have to respect certain laws in order not to lose information. And therefore, we apply the Nyquist theorem so that we can sample the signal and be able to reconstruct the signal without losing information. So again, Nyquist theorem, keep that in mind. We'll come back to it. We'll refresh on it. But again, choosing the sampling time, how fast we're going to be taking these samples, is not random, and we have to follow rules in order to ensure the signal can be reconstructed without losing information. Of course, these rules apply to an ideal signal, a signal that is band limited, and a signal that exists from negative infinity to infinity. So there is an ideal situation and there is a practical situation where the signal does not exist from negative infinity. The signal does not have a finite bandwidth. And therefore, when we are doing the sampling, practically, we're going to be sacrificing some content of the signal, because again, the signal is not ideal. And nevertheless, if we understand what is it that we're sacrificing, we can minimize the losses that we're gonna incur if we apply the sampling. And the same thing also applies with the quantization. I can always use an infinite number of quantization, but that will not be practical. I can then say, okay, I'm gonna use 10,000 number of quantization. Then somebody's gonna say, oh, what do you need all that for? You're just measuring the temperature. You only need few digits. You don't need that accurate of a measurement. You're wasting your bandwidth, you're wasting your space, you're wasting your memory. So there is always a compromise, and there is always an engineering sense that goes into choosing all these parameters. I should not be choosing more levels to represent a signal than I need to, because I'm going to be paying for it with the memory, with the processing, with the extra processing, and therefore you should optimize all these parameters. Okay, so what is the control problem? Similar to what we discussed at the beginning of our class, we usually look at this feedback loop and discuss the control problem. Now, as everybody can guess, if the system and the plan that I'm trying to control does not change with time, I can always find a controller that will behave exactly the way you want it to behave. You don't need to do all this work and feedback and controller and change the controller. If the plant is gonna always behave exactly the same, I can just tell you, apply this much voltage to the input and you're gonna get the response that you want. However, in practical term, any system that we're gonna deploy is gonna be subjected to disturbances, is gonna be subjected to uncertainties in the modeling of the system, is going to be subjected to nonlinearities of the system, is going to be subjected to noise that is added to the system, and therefore it's going to be impossible to predict exactly how the system is going to be at any instance in time. And that's why we use, that's why we need the feedback, and that's why we need the controller. Does that make sense? So keep that also in mind. And this is also fundamental later on, when you feel like, oh, why we're doing all this? I mean, if I know this plant and I can just apply a signal, why do I need to do all this feedback? Keep in mind, because the bigger picture, this plant that you're going to deploy, you might design it at the lab temperature or room temperature, but it might have to work in a colder environment, a hotter environment. Therefore, the whole system that you're trying to control might behave slightly differently, and we might not get exactly the signal that you are expecting from it. And therefore, with the feedback and the controller, you can try to make up or compensate for all these other factors that come into the system. Okay, so again, the parameters that we'll be focusing on is the steady state errors. I want my response as accurate as possible. I want my system to be stable. I want my transient response to be according to what I want. I'm not going to say what the transient response, because it's going to depend on what you're trying to control. I might want it to be very fast. I might want it to be slower. I might want it to be have a short settling time, a short rise time. And again, all these are relative depending on the system that you're trying to control. Okay. Now also, if you recall, just like with the design of any system that we do, in order to design and implement a controller, it's an iterative process. We're gonna come to the plan that we're trying to control. We're gonna choose the sensors that gonna be taking the measurements and providing the feedback. We're gonna choose the actuators that gonna drive the plant. We're going to be developing a model that will represent, you know, all the components, the plant, the sensors, actuators, etc. Then we're going to be designing, or we're going to be analyzing the model. Then we're going to be designing a controller. Then we're going to evaluate the design analytically using MATLAB. And then we're going to be testing the system and make sure it meets the specifications. If it does not, then we're going to iterate through the controller again and tune it till we meet the specifications. Does that make sense? So again, I don't want, I want the expectations to be clear. When we design a controller, it's not, oh, this is the controller, it should work 100%, go implement it. No, we're gonna test it, because when it comes to applying it to a physical system, you might have approximated the system by a second order system and you designed everything accordingly. But your system is not really a second order, and there is a third pole there that you have to account for. And therefore, you know, you might have to go back to your controller and say, oh, now I have to account for that extra pole that is now showing up when I am applying this signal. Does that make sense? So it's always an iterative problems. And even probably you will see it even in some of the problems that we will do. We'll design a controller thinking this should behave exactly somewhere, and then, you know, when we try to implement it, we say, oh, it did not. I mean, it might have got us closer to what we want, but it did not exactly do exactly what we want, because there is, you know, a zero here that we should account for, or there is a pole there that we approximated, or we consider the impact of it very, very small, and therefore a third order system or a fourth order system that we approximated by a second order system, and, you know, now it's showing up, and therefore we have to go back to the drawing board and update the controller. Make sense? Okay. So let's look at an example of a model of a system. Now, I imagine, I mean, all of us are familiar with modeling a system, a simple physical mechanical system or an electrical circuit. I mean, we covered that in details in our control class. So therefore, if I look, you know, here's a servo motor that is driving an inertia and a damping load. And if I look, if I want to get the model for this system, I'm going to use, you know, relates the different components together. The torque that the motor generates is proportional to the current. The torque is going to be connected to a mechanical load, and therefore is going to be proportional to the inertia and the damping on the load. And therefore I'm going to be using an electromechanical conversion, Newton's laws. Then I can relate the voltage here using Kirchhoff voltage laws. So again, the point I'm trying to make here is we're using Kirchhoff voltage laws, Newton's laws, and energy conversion laws in order to come with a model that relates all these components together. So if we were to put all these components together, I'm going to get the relationship between theta from the motor, the servo motor, and the voltage that I am applying to that motor. And therefore, now, I mean, this is, I have this in the backup, so you can always go back if you like. And I mean, if you do not remember it, or it does not ring a bell, we've seen something similar in control. So I took a screenshot from the control class. You can always look at it, you know, how to get the theta over the applied voltage relationship. But nevertheless, the point I'm trying to make is that we can, after we do that, we can come up with a model that represents the theta over the applied voltage. These are the parameters. Some parameters are of the circuit, some parameters, of the motor, some parameters from the load. Nevertheless, if I look at this, this is a second order system, and I know it's a second order because I have S multiplied by S, which is S squared. And of course, in this case, I ignored the impact of this inductance. So this inductance and ignored the impact of it, and therefore I got a second order. If I did not, if you look here, if I kept it, then I would have gotten a third order system. So this is an example where we try to model, we try to simplify the model, and we try to control. If things work, then maybe our simplification was valid and everything works. Maybe we try it and then realize this inductance, I could not ignore it anymore. I have to update my design in order to account for it. Okay, so nevertheless, here is an example of using that servo motor to drive an antenna. So we have the motor that we just modeled before, and then we connected this to some gears that is able to drive an antenna and rotate it. And we took a measurement of the position of the antenna, we fed it back, so there's a voltage that is proportional to the angle of the antenna. So we're controlling the angle of the antenna, and we have a voltage that is applied that is proportional to how we want the where do we want the antenna to be. We take the difference between these two, that is going to give me an error signal. Of course, also one thing I want to mention, when we see an error signal, usually we associate error with a negative, something that is negative. Nevertheless, this error signal is something that we like, that we want to generate. So there's nothing in error here other than the difference between where we want and what actually, where the antenna is the difference between them is, we refer to it as the error signal. Now this error signal might be a very small signal, and therefore I might have to use a power amplifier in order to amplify that signal. And therefore I apply this to an amplifier, and then if I were to model the whole system, I'm gonna get a diagram that looks something like this. This is the model of the servo motor, this is my amplifier, and this is my sensor. And if this sensor is fast enough, I can just make it just a 1. Now one thing, just to mention here, is that this amplifier, just like any other components, might behave linearly within a range, and then it will saturate. So this graph on the right shows the behavior of this power amplifier. So this power amplifier, if you apply a voltage between negative 4.8 and 4.8, it's linear, it's going to multiply the signal by 5. But then if you apply any voltage above this value, the system is going to saturate. So you can see how this system within a certain range is going to behave linearly, but outside of that range is going to behave non-linearly. But you also realize if I'm applying the signal, if I'm deploying this system, I might be behaving most of the time within the linear region, but during a transient response I might be saturating the amplifier. Make sense? Now this might be acceptable, it might not be acceptable, but again, that's why we need this iteration process. I might look at this and say, oh, because the amplifier is saturating, it's causing a behavior that is not acceptable. Or it might be, because it's saturating, it's making the response faster, and I'm seeing a little bit of oscillation, but this is acceptable considering it does not last a long time, for instance. Again, the emphasis is the importance of iterations and testing and going back and ensuring that the design meets the specifications. And again, different specifications might be different depending on the system. Okay, so here is another line drawing robot that at least we have one engineer in our class. We're going to be doing something similar to in their project. So again, this is trying to control these 3 angles of the robot arm, and this is using and this is the model of the robot arm. So again, taking the motor, so we have 3 motors here that control theta C, theta B, and theta A, and this is the model, our model for the servo motor. And then we adding some gearbox to change the torque or the ratio of the rotation, the speed of the rotation, and we're applying a power amplifier in order to control the servo motor. So this is from a digital computer. I'm taking a digital signal. The computer is not going to be able to drive the motor, so you might have to take that small signal, take it to a power amplifier, and use that to drive my motor. Okay. Sounds good. So this is what we're going to be doing throughout the semester. Now this course is going to uses lots of math. Nevertheless, that math is usually associated with a real-time systems example. So therefore, the math hopefully will be more fun. And again, lots of the system we're using, or lots of the models and the system and the math that we're using, we should always be able to go to MATLAB and test it and run it and verify it. So that also makes it more or easier to absorb and understand. And we'll try to use as much MATLAB. Again, this class does not have a lab, which is unfortunate. Nevertheless, this is the best we can do. But usually if there is a lab, then we can take everything that we learn and apply it and see it in action. And that's why we added the project, in order to complement all the theoretical material and see it in action. Nevertheless, we're going to be also try to use MATLAB in the class and MATLAB in some assignments. So also you can become also more familiar with the tools that you can use to study the materials. Any questions? Questions? So again, to reiterate what we started with, we said we're gonna do asynchronously. We're gonna have every week on Sunday, I'm gonna be posting modules. I'm gonna try to make the modules as short as possible, and it doesn't mean the module is short, but I can have more of them. So the overall length is the same, but rather than record like an hour and a half, I'll try to break it so you can, you'll have more flexibility when you watch it. And once you watch modules, we'll have also a homework at the end of the modules. You can do the homework, and if you're in good shape, that's great. If you feel you need, help, or there is something that we covered that is not clear, or that is that you need more help with, let me know. Now, if it is only you, we can schedule a one-on-one. If it is something that I feel like, lots of people did not understand this, I might, add another module, or we can schedule a review session, and we can have a live session. Again, I'm hoping the asynchronous will work for the most of you. It will give you the flexibility. Never you're gonna have the commitment. It gives you the flexibility if you're working, if this time is not the time that you really like to be awake, and if you're doing most of your study at night. Again, this will give you the flexibility of trying to do it whenever you can. Nevertheless, we're gonna have lots of modules by the end of the semester, and please do not let the modules pile up. Try to do it religiously on a weekly basis. Don't let the modules, if you skip a week, it's going to be much harder for you to catch up, because you're going to have the week and the week before, and if you have 5-6 modules, you have to review from the previous week, and then 5-6 of this week, and you have to understand the previous material to get this material. You're just going to make it harder for you. So please try to do it religiously. Again, hopefully this will work. Nevertheless, I'm open for feedback. If we, at later point realize, this is really not working, we can always come back and do it differently. Sounds good? Again, I'd like to welcome you all, and hopefully you will have a great summer, a very beneficial summer, and I hope you will enjoy this class. And I think it's, in my opinion, it's one of the fun classes. So hopefully lots of you are gonna really enjoy this class.
Will you be uploading the slides?
I'm gonna be uploading the slides, the handouts, and the videos, yes.
Okay.
Sounds good, everybody. Thank you all, and we'll exchange emails, and if you have anything, just reach out and let me know. Thank you.
You want to see my project real quick?
Yeah, sure. I mean, you're more than welcome to do it for your project for this class too.